The National Electrical Code, or NEC, does not specify a minimum required distance for the perimeter ground loop to extend out from the building. However, it does provide guidance on ground grid design and installation. Article 250.56 covers grounding electrode systems. Paragraph C states metal underground structures and metal water pipe. Any non-electrical metal underground structure or metal underground water pipe within the premises shall be bonded to the grounding electrode system. Paragraph D states other electrodes. Where other electrodes, such as concrete encased electrodes, ground rings, or pipe electrodes, are present at the premises, they shall be bonded together to form a grounding electrode system. NFPA 70E, Standard for Electrical Safety in the Workplace, 130.2, paragraph C, item 1 states that equipment grounding conductors shall be connected to the equipment grounding conductor system at the service, at each panel board, and at each separately derived system. 250.120, paragraph A, item 1 states that the equipment grounding conductor shall be connected to the grounding electrode system at the service equipment at each panel board, and at each separately derived system. IEEE Standard 1100, Recommended Practice for Powering and Grounding Electronic Equipment, Section 5.1 provides recommendations for ground grid design, but does not specify a minimum distance for the perimeter ground loop. Table 5.1 provides guidance on the minimum number of ground rods and their recommended spacing. While there is no specific code or standard requirement for the minimum distance of the perimeter ground loop, it is generally recommended to extend the loop at least 3 feet outside the building footprint. This distance provides a sufficient buffer zone to mitigate the effects of lightning strikes, ground faults, and other electrical disturbances that may occur near the building. The soil conditions at the site may influence the minimum distance of the perimeter ground loop. Dry or rocky soil may require a larger buffer zone than moist or clay-rich soil. The presence of buried utilities such as gas lines and water mains can affect the placement of the perimeter ground loop. If the building is expected to be expanded in the future, it may be prudent to extend the perimeter ground loop beyond the current footprint to accommodate future growth. When designing a ground grid, you're essentially creating a low impedance path for fault current to return to the source, and also providing a means to equalize potential within the grid area, minimizing step and touch potentials. The primary goal is safety, protecting personnel and equipment from dangerous voltage gradients during fault conditions. Now, while the NEC doesn't explicitly state a minimum distance for the perimeter ground loop from the building, several factors influence its optimal placement. Let's delve into those factors. Firstly, soil resistivity plays a crucial role. Soil resistivity is the measure of how well the soil conducts electricity. Low resistivity means better conductivity. In areas with high soil resistivity, such as those with dry, sandy, or rocky soil, you might need to extend the ground loop further out to achieve the desired grounding impedance. This is because the current disperses less effectively in high resistivity soil, necessitating a larger area for dissipation. Conversely, in areas with low soil resistivity, like those with moist clay soil, a smaller perimeter loop might suffice. Secondly, the size and type of the building matter. A larger building generally requires a larger ground grid to adequately cover its footprint. The type of building, particularly its electrical load and sensitivity to electrical disturbances, also influences the design. For instance, a data center or a hospital, which houses sensitive electronic equipment, might require a more extensive ground grid than a warehouse. Thirdly, consider the presence of underground utilities. Before installing the ground grid, it's imperative to identify the location of all buried utilities, such as gas lines, water pipes, and communication cables. You need to maintain a safe distance from these utilities to prevent accidental damage during installation and to avoid creating potential hazards. Consult local regulations and utility companies for specific clearance requirements. Fourthly, think about future expansion. If there's a possibility of future expansion of the building, it's wise to extend the ground grid beyond the current footprint to accommodate the potential increase in electrical load in the area. This proactive approach can save significant costs and effort in the long run, as it avoids the need to modify the ground grid later. Fifthly, consider lightning protection. In areas prone to lightning strikes, the ground grid plays a vital role in dissipating lightning current safely into the earth. The perimeter ground loop should be designed to effectively intercept and conduct lightning current away from the building. This might involve extending the loop further out and incorporating additional ground rods or electrodes. Sixthly, adherence to industry standards and best practices is essential. While the NEC provides general guidelines, other standards, such as IEE Standard 1100, offer more detailed recommendations for ground grid design. Following these standards ensures that the ground grid meets the required performance criteria and enhances its reliability. Now let's talk about the components of a typical ground grid. Firstly, ground rods or electrodes. These are typically copper-clad steel rods driven vertically into the earth. They provide a direct connection to the earth and serve as the primary means of dissipating fault current. The number, size, and spacing of ground rods depend on the soil resistivity and the desired grounding impedance. Secondly, ground conductors. These are typically bare copper wires or cables that connect the ground rods and form the grid network. The size of the ground conductors must be adequate to carry the maximum fault current without overheating or causing excessive voltage drop. Thirdly, connections. Proper connections are crucial for the integrity of the ground grid. All connections between ground rods, conductors, and equipment must be made using approved methods such as exothermic welding or compression connectors to ensure a reliable and low-resistance connection. Now, let's explore some common ground grid configurations. Firstly, the grid configuration. This is the most common configuration, consisting of a network of interconnected ground conductors forming a grid pattern. The grid provides multiple paths for fault current to flow, enhancing its effectiveness. Secondly, the ring configuration. This configuration consists of a continuous ground conductor encircling the building. It's often used in conjunction with ground rods to provide a low-impedance ground path. Thirdly, the radial configuration. This configuration consists of ground conductors radiating outward from a central point. It's typically used for small buildings or equipment installations. Now let's delve into the installation process. Firstly, site preparation. Before starting the installation, clear the site of any obstacles such as vegetation, rocks, and debris. Ensure that the soil is properly compacted and leveled to provide a stable base for the ground grid. Secondly, ground rod installation. Drive the ground rods vertically into the earth to the required depth. The depth depends on the soil conditions and the desired grounding impedance. Typically, ground rods are driven to a depth of at least 8 feet. Thirdly, conductor installation. Lay the ground conductors along the planned grid pattern. Ensure that the conductors are in direct contact with the soil to maximize their effectiveness. Fourthly, connection. Connect the ground conductors to the ground rods using approved methods. Ensure that all connections are tight and secure. Fifthly, testing and commissioning. After completing the installation, test the ground grid to verify its performance. Measure the grounding impedance and compare it to the design requirements. Make any necessary adjustments to ensure that the ground grid meets the required specifications. Regular maintenance is crucial for ensuring the long-term effectiveness of the ground grid. Inspect the ground grid periodically for any signs of damage or corrosion. Repair or replace any damaged components promptly. Retest the ground grid periodically to verify its continued performance. Now let's discuss some common challenges in ground grid design and installation. Firstly, soil resistivity variations. Soil resistivity can vary significantly across a site, making it challenging to achieve uniform grounding impedance. Conduct thorough soil resistivity testing to identify areas of high resistivity and adjust the ground grid design accordingly. Secondly, buried utilities conflicts. The presence of buried utilities can complicate the installation of the ground grid. Coordinate with utility companies to identify the location of buried utilities and adjust the ground grid layout to avoid conflict. Thirdly, limited space constraints. In some cases, limited space constraints might restrict the size and layout of the ground grid. Consider alternative grounding methods such as chemical ground rods or ground-enhancing compounds to improve grounding effectiveness in limited space conditions. Fourthly, corrosion concerns. Ground grids are susceptible to corrosion, particularly in aggressive soil environments. Use corrosion-resistant materials, such as copper-clad steel or stainless steel, and apply protective coatings to minimize corrosion. Proper design and installation of a ground grid are essential for ensuring electrical safety and protecting equipment from damage. While the NEC doesn't specify a minimum distance for the perimeter ground loop from the building, careful consideration of factors such as soil resistivity, building size, underground utilities, future expansion, and lightning protection is crucial for determining the optimal placement. By following industry standards and best practices, you can create a reliable and effective ground grid that meets the specific needs of your application. I can add a few extra details and considerations that might be helpful when designing a ground grid. Let's expand on the topic of soil resistivity testing. Conducting a comprehensive soil resistivity survey is a critical first step in ground grid design. This involves measuring the soil resistivity at various locations and depths across the site. There are several methods for measuring soil resistivity, including the Wenner 4-pin method and the Schlumberger method. The data obtained from the survey is used to create a soil resistivity model, which is then used to optimize the ground grid design. The model helps determine the optimal number, size, and spacing of ground rods, as well as the size of the ground conductors. In addition to soil resistivity, it's also important to consider the soil composition. The presence of certain chemicals or minerals in the soil can affect its corrosivity. For example, soils with high concentrations of chlorides or sulfates can be particularly corrosive to copper. In such cases, it may be necessary to use corrosion-resistant materials or apply protective coatings to the ground grid components. Another important consideration is the depth of the water table. The water table is the level below which the ground is saturated with water. The depth of the water table can affect the grounding impedance as well as the corrosivity of the soil. In areas with a high water table, the ground grid may need to be designed differently to account for the increased moisture content. The presence of nearby metallic structures can also affect the performance of the ground grid. Metallic structures such as fences, pipelines, and underground tanks can act as grounding electrodes and influence the distribution of fault current. It's important to bond these structures to the ground grid to ensure that they are at the same potential as the surrounding earth. This helps prevent dangerous voltage gradients from developing near the structures. In areas with high lightning activity, it's essential to design the ground grid to effectively dissipate lightning current. This may involve extending the perimeter ground loop further out, adding additional ground rods, and using surge protection devices. The goal is to provide a low impedance path for lightning current to flow to earth, minimizing the risk of damage to the building and its contents. When designing the ground grid, it's also important to consider the potential for electromagnetic interference, or EMI. EMI is unwanted electrical noise that can disrupt the operation of sensitive electronic equipment. The ground grid can help mitigate EMI by providing a low impedance path for noise currents to flow to earth. To minimize EMI, the ground grid should be designed to be as symmetrical as possible and should be connected to the building's electrical system at multiple points. The ground grid should also be isolated from other metallic structures to prevent noise currents from flowing through them. Regular inspections and maintenance are crucial for ensuring the long-term effectiveness of the ground grid. The ground grid should be inspected at least annually for any signs of damage or corrosion. Ground rods should be tested to ensure that they are still making good contact with the earth. Connections should be checked to ensure that they are tight and secure. Any damaged or corroded component should be repaired or replaced promptly. In addition to visual inspections, it's also important to perform electrical testing of the ground grid. This involves measuring the grounding impedance and comparing it to the design requirements. The grounding impedance should be measured under both normal and fault conditions to ensure that the ground grid is performing as expected. If the grounding impedance is too high, it may be necessary to add additional ground rods or improve the connections. Designing a ground grid is a complex process that requires careful consideration of many factors. By following industry standards and best practices, and by paying attention to the details, You can create a ground grid that provides reliable protection for people and equipment.